Are you able to see the PPT?
Yes, ma'am.
Okay. So if I'm asking you some questions, please answer, okay? Okay, we'll start with the subject, okay? The subject code is 19R 2015, and the subject name is Neural Networks and Fuzzy Systems. Okay, and that's what do you mean by neural network? See, it is just an information processing system. Okay, and the concept behind this is the biological nervous system, which is nothing but the brain. So they've taken this brain process information as an example in order to frame this artificial neural networks. So what this is going to do, it's going to understand and translate the data that is being input, that is data that is being given in one form, such that we'll get the output in another form. Okay, so whatever input we are going to give, this artificial neural network is going to understand it and then translate it, and the output is going to be in the form of zeros and ones. Okay, and then it's going to translate it such a way that we are going to get the desired output. So this is the main job of an artificial neural network. And the example for this is brain process information. And here you can see the architecture of a simple artificial neural network, that is a neuron. Okay, that's X and Y, it represents the input nodes, and Z represents your output node. Small x and y is your input, and then A and B are your weights, and the O represents your output. Okay, and then I told you that this artificial neural network is compared to that of a biological neural network. Biological neural network is nothing but your brain. So what they say is, see, you can see the picture of this neuron, okay, which is found in the brain. See, it consists of many interlinked neurons. Okay, I've just given you the picture of just one neuron. And what they're telling is what? This neuron is going to act as a highway or a pathway for information to be transferred from one point to another point. Okay, so that is based on the based on which, see, I told you that it's interlinked neurons. So many neurons are going to be present. Okay, so the brain knows which path to take, such that your information is passed from one point, that is point A to point B, in a fastest way. Okay, so it will take a different route. Okay, we could not imagine, or we cannot think, so this route only this neuron is going to take. So we can't even imagine. So the brain, it knows that which path to take. Okay, so it will take a different route, whichever is the fastest route and easiest route, to transfer information from one point to another point. And these are the parts. Okay, it's got a dendrite, and then it's got a cell body, and then it's got terminals. So dendrite will act as the receiver. Okay, so it will receive all the input signals, and then information is passed to the axon or the cell body. Inside this, you have the nucleus, the black dot. Okay, and then to the terminals, and to the end of the terminals, we have the synapse, that round dot thing. Okay, that is which is attached to the end of the terminals, and this is going to act as an interconnection to the other neurons. Okay, and then I told you that it's going to have three parts. Okay, first one is dendrites. Okay, these are connected to the cell body. Cell body is nothing but the body of the neuron. Okay, it is also, cell body is also called as soma, and this cell body is the one which is going to process all the information. Okay, and cell nucleus, that round dot, right, the big dot, it is located in the cell body, that is called as a nucleus. And then comes the axon. So axon and cell body, axon comes under the cell body. Okay, axon and nucleus together form the cell body, and this axon will carry the impulses or electrical signals of the neuron, okay, to the terminals. And the terminals, this is the end part. Okay, this acts as what? A network which is used to connect to the other neurons. And I told you that to the end of the neuron, what happens? We can find a bulb-like organ which is called as the synapse. This is the one which is going to interconnect to the other neuron. Okay, and I told you that electrical impulses are passed between the synapse and the dendrites. Okay, dendrites are going to act as the input terminals. Okay, it's going to act as the receiver, and synapse is found at the farther end of the terminals. Okay, and then these synapses are of two types. First one is inhibitory. The second one is excitatory. Okay, excitatory, what it's going to do? It is going to fire the neuron, next neuron. That is the neuron which is being connected. Okay, it's going to fire the neuron. It's going to cause firing. Whereas inhibitory, what it's going to do? It's going to stop the firing. It's going to obstruct the firing. So it's going to hinder the firing of the receiving cell. Okay, and after a pulse is being carried by the axon fiber, it will remain in a state of rest for some time. So that period is called as refractory period. These are all fundamentals, okay? You all would have studied already, okay, in your school. So I'll just brush up with it, okay? So that period is called as refractory period. That is, axon is going to carry the impulse, the center part, that lengthy part, okay? It is going to carry all the electrical impulses or the electrical signals. And once it carries a signal, it's going to remain in a state for some time. And that period is called as the refractory period, okay? So what this, I've just given the picture of just single neuron, okay? And this is how information is going to flow. How it is going to flow? The dendrite is going to be the receiver. It is going to receive all the incoming signals. And then this impulse or the electrical incoming signals are being passed to the terminals through the cell body or the soma. Okay? And these terminals are going to receive the electrical impulses. And then the end part of the terminals is your synapse, which acts as the interconnection to the other neurons. Okay? And through this synapse only, signal is being passed to the next neuron. Okay? This is how information is being passed from the dendrites to the terminals, or from one neuron to the other neuron. Then we are going to study about the artificial neural network, right? See, this artificial neural network model is completely based on this biological neural network. Okay, so the dendrites are compared to that of the input node in an artificial model, ANN model. Okay, cell body concept is for the hidden layer, and the terminals concept is for the output node. So we are going to have 3 nodes in the artificial neural network. The first one is input node, the second one is hidden layer, and the third one is going to be the output node. Okay, and what this ANN, what are the applications in which this ANN is being used? First one is pattern matching, classification, optimization function, approximation, vector quantization, data clustering. So these are the applications where this neural network is being used. Okay? And then this is the first topic in our module 1. So it's the difference between ANN and BNN. ANN is for artificial neural networks and BNN is biological neural networks. Okay. The first thing is it's faster than ANN. Okay. Biological neural network is faster than ANN. But ANN is slower than BNN. The only reason and the comparison is based on this, on what is BNN is natural. Okay. It's naturally made. But ANN is artificially made. Okay, based on that reason only they've compared it. Okay, and BNN stands for biological neural network, and ANN stands for artificial neural network. Okay, science and complexity are more in BNN. So that is, they're comparing it with the brain, right? But size and complexity are less in ANN because it's based on the application. Brain is going to do lots of work, but an ANN, artificial neural network, is just what? It is just created to perform just 1 or 2 applications, okay? It's not going to perform all the applications. It's application oriented. Storage capacity or memory of BNN is more, and ANN it's very less because it's artificially made based on the application. BNN is less adaptable, ANN is more adaptable because we are only going to create it, okay? So it is more adaptable. Fault tolerance of BNN is more in fault tolerance is more in biological neural network, but it's very less in artificial neural networks. Okay, and then control mechanism is complex in biological neural network, where it's very simple because we are only going to create it. We are going to write the program, whatever be, we are going to do it, right? In ANN. So based on the application only, we are going to do it. Okay, so that is the difference between artificial neural networks and biological neural networks. So this might be asked for 7 marks, okay, in your exam. And then, okay, let's have a look at the neural network architecture. Okay. See, these neural networks are complex structures. Even though humans are going to create it, it is going to be complex structure. Okay, but when compared to BNN, it is less complex. Okay, and this ANN is made of artificial neurons. Okay, which can take in multiple inputs, n number of inputs, in order to produce a single output. Okay, can give n number of inputs in order to get a single perfect output. That is the job of a neural network. Okay, it's going to have an input layer, it's going to have an output layer, and then a hidden layer. It might have one hidden layer or multiple hidden layers, which is everything is based on the applications. Okay, and why it is called as hidden layer? because it is hidden from the external world. That is the main reason it is called as a hidden layer. So this is called as an artificial neural network. Okay, and it's going to function just like a human brain. Okay, and one more thing, what they're telling is all the neurons influence each other. What is the reason? I told you that all the neurons are interconnected in a brain, okay, through the synapse. The same thing is going to happen in artificial neural networks. So all the neurons here are what? The input layer, output layer, and then the hidden layers. Everything's got neurons, right? All are interconnected, so they're going to influence each other. Okay, and this network, what it can do is it can acknowledge, and then it can perceive every aspect of the data set. That is the relationship between the neurons. That is the input data and the output data. So it can do everything. Okay, and then they're also capable of finding solution for extremely complex patterns, because it is the human beings who are going to create it. Okay, we're going to create it based on the application. So these artificial neural networks are capable of finding solution for complex patterns. Okay, and this is the architecture for the artificial neural networks. And it's got one input layer, one output layer, and in between it's got two hidden layers. Okay, and this is how the information will flow. That is from input layer to the output layer through the hidden layers. In between, you'll have some weights and bias. Okay, and then these are the components of a basic artificial neural networks. I told you that we have inputs x1, x2, x3, and xn. It represents the input nodes. Okay, and then comes the summation function. So what the summation function is going to do? See, the input that's being given to the summation function is based on the product of this input value and the weight value, x1 into w1 plus x2 into w2 plus x3 into w2 till x plus xn into wn plus the bias. So also we are also going to add the bias to it. Okay, and then this is then given to an activation function, and the output of this is going to be a bipred, which is going to be the output of this artificial neural networks. So these are the components. The first thing is what? The first component is what? Input. It represents what? x1, x2, x3, and x up to xn. Okay, these are the values which we need to predict output value, which are being given to the neuron. Based on these inputs, we are going to get an output. Okay, and then comes the weights. Okay, weights and bias both are being given to the summation function. I told you what these weights are going to do. It is going to increase the steepness of the activation function. Okay, whereas bias is going to move to the left or to the right, such that the proper neuron is being triggered. Okay, and you also get the desired output. So it is the getting the desired output is based on the neuron that is being fired. That is, it is based on the updation of the weights and the bias. So that is the important factor, okay, which has to be considered. Then comes the summation function. What it is going to do? It is going to add all the weights and the bias, weights multiplied with the input signals or the input values, and then it is summed up. It is then added up. That's the work of the summation function. Okay. Then comes the activation function. What this activation function is going to do is it is going to decide which neuron to fire. So that is based on the activation function. Okay. So activation function, what is going to do? It is going to decide which neuron to fire. Okay, based on the application. So actually, the flow of information in a neuron, in an artificial neural network, it occurs in two ways. The first one is, so based on this flow of information, we can we can say the first type is what? Feed forward network, and the second type is going to be what? Feedback network. It's also called as back propagation network. Okay, so feed forward network, in the sense information is going to flow in one direction, that is from input to the output alone. So it might have hidden layers or it might not have hidden layers. It can also have, that is that there might not be any hidden layers, or it can have multiple hidden layers. That is what it means. But information is just going to flow from input side to the input node to the output node. Okay, and they're used mainly for pattern recognition. And below this, you have two types: single layer feed forward network and multi-layer feed forward. In single layer feed forward network, you're just going to have the input layer and the output layer. Okay, and information is going to be passed from input layer to the output layer. Whereas in a multi-layer feed forward network, information is going to be passed the same thing, input layer to the output layer, but in between you will have multiple hidden layers, either one or n. That depends upon the application. Then comes your feedback networks. Okay, feedback networks in the sense, what we're going to do is we're going to, based on the input, we're going to get an output. And then if that output is not being decided by the person, what we're going to do is we are going to adjust see feedback, we are going to take the output signal and then we are going to calculate the error. We are going to compare it with the desired output. Okay. And if there's going to be some difference based on that error value or the difference value, we are going to change the values of the weights. Okay. Such that, and the weights are adjusted till you get the desired output. You all know what is meant by feedback, right? That is what is happening here. So based on this, this feedback network is again classified into single node with its own feedback. Okay. Single layer recurrent network and multi-layer recurrent network. So these are the three types. And here information is going to pass in both the direction, that is forward direction as well as backward direction. So through the backward direction, it's because of the feedback loop. Okay. And the details about these nodes and these different types of nodes is given in the link that is given below. Okay. And then comes the activation function. So this is the third topic. The first topic was difference between BNN and ANN. The second topic was the architecture of artificial neural networks. And then the third topic is the activation function. Some of the common activation functions that are being used in artificial neural networks. Okay. So what is an activation function? I told you that this activation function is only going to decide, okay, which neuron to fire. So that is based on the values of the activation function. And this is used to get the output of a node. Okay. This will decide whether a neuron should be activated or not. And all these things are based on the what? Summation function. I already told you, right? Summation function says input to the summation function is going to be what? Product of the input values or the input signals and the weight. And then you're going to add bias to it. Okay. And this is also called as the transfer function. And why do we go in for this activation functions? Okay, the main purpose of going in for this activation function is to introduce non-linearity into a neuron. Suppose if it's going to be linear in nature, and when we are going to take derivatives of it, or if we are going to perform some operation in it, it's going to become stable, sort of stable. You won't be getting the desired output. So that is why what they are telling us, in order to be more practical or experimental, we're going to introduce some non-linearity into the neuron. So that is why we go in for activation functions. Okay. And these activation functions are basically divided into two types. First one is linear activation function. And the second type is non-linear activation functions. Okay. Linear activation function is also called as the identity activation function. Okay. Linear or a line. Okay. And then the equation is what? Fx is equal to x. And the range, it varies from minus infinity to plus infinity. Okay. And where it is being used, it's used just in the output layer alone. Nowhere else this is being used. Okay. And one of the issues that is being faced when you go in for this linear activation function is what? Okay. The result with what happens is, if you're going to differentiate this linear function, okay, in order to become non-linear, I told you that linear function, see, to become non-linear, what happens? It's going to become a straight line. It's going to become a straight horizontal line, which means that the input is going to be stable. Okay, there is not going to be any variation or changes in your input. That is why they're telling that this linear activation function is not going to be used. Even though it's going to be a linear function, we are going to include some non-linearity into the artificial neuron. That is why we go in for this activation function. So this is the first type, linear activation function or identity activation function. Then the next type is what? Non-linear activation function. This is what is being used, mostly used, okay? Okay. And then some of the terminologies used to know is derivative or differential. So here what they're going to do is, in a linear, non-linear activation function, they're going to differentiate the value or we're going to find the derivative. Okay. So the first terminology is what? Derivative or differential. That is change in y-axis with respect to change in x-axis. That is what we know, right? dy by dx. That is called as derivative or differential. This is also called as slope. So you can see a diagram of this non-linear activation function. So for each and every point or each and every data, what they're going to do is they're going to find the differential value or the derivative. That is, they're going to draw a slope to it. That is what is called as derivative or differential. See, it's going to be a non-linear function or non-linear data, they're going to linearize a non-linear data. Okay. And then comes a monotonic function. This shows whether the data is increasing or whether it's non-increasing or non-decreasing, or it's going to be stable. Okay, that is what these are the two terminologies you should know. Okay, derivative or differential. Okay, it's nothing but the slope, and then monotonic. Okay, is either it shows whether the data is or the function is entirely non-increasing or non-decreasing. Okay, and then under this non-linear activation function, we have 4 types, and that is based on the range or the curves. Okay, the first type is going to be sigmoid or logistic activation function. Tanh activation function, are linear, rectified linear unit function, and then softmax function. So these are the 4 types. So the sigmoid or logistic activation function, sigmoid activation function or the logistic activation function. So for all the 4 types, you should learn the equation, nature, and then the range, and where it is being used. Okay, so these are the 4 points you'll be studying in all the 4 types. The equation is what? A is equal to 1 by 1 plus e to the power minus x. This comes in a non-linear activation function, so it's non-linear in nature. Okay, and the range they're telling us is from 0 to 1. Okay, this is the range of this activation function. See, suppose if the range is going to increase, they're telling that the values are going to be steep. That's why they're setting the value to 0 to 1. And this is used, and one of the applications of this type of activation function is what? It's being used in binary classification. Okay, that's binary classification of binary is what? 0 or 1. Okay, so what they're telling us, the answer or the result can be easily predicted. That is, if the value is going to be, the range is going to be 0 to 1, right? If the value is going to be greater than 0.5, the output is going to be 1. If the output result is going to be less than 0.5, the output is going to be 0. Okay, so it's being used in binary classification. So the binary values are 0 and 1, and the range is what? 0 to 1. If the value signal, if the impulse is going to be greater than 0.1, the output is going to be 1, and it's going to be less than 0.1, the output is going to be 0. Okay, then comes tanh or hyperbolic tangent activation function. Okay, and then the equation for this is what? Tan h of x, tan h, right? Given by 2 by 1 plus e to the power minus 2x minus 1. And here the range they're telling is it's going to be minus 1 to plus 1. Nature is what we know. It is non-linear in nature. And this is being used in hidden layers. The previous type was being used in what? Output layers. Here this is being used in hidden layers. Okay, and the range is what? Minus 1 to plus 1. Okay, and if it is close to 1, we can say that hidden, see if the value is going to be 1, we can say that the hidden layer is going to be very close to it. Okay, because of this, we can focus the data. Okay, and then we can bring out the exact desired values. Okay, so if you get the desired value, this will make learning for the next layer very much easy. Okay, so if the mean value, that's what they say, okay, the range is between minus 1 to 1, okay, and if the mean value is going to be very close to 0, what happens? It will make the learning for the next adjacent layer become easy. Okay, and then the third type is what? ReLU function. This is rectified linear unit, and this is the most widely used activation function. Okay, and this is also implemented mostly in hidden layers, just like the previous type. And you should learn the equation. Range is between what? 0 and infinity. Nature is what? Non-linear in nature. Okay, here what they're telling is what? You can have multiple hidden layers or multiple in-between neurons. That is multiple hidden neurons in between your input layer and your output layer. Okay, and what they're telling us, this RE, rectified linear unit, is what? It's very much expensive it's less expensive when compared to the first 2 types. Okay, because whichever neuron has to be activated based on some computations or mathematical operations, only those particular neurons are going to get activated. So they're telling that it's going to be less computationally expensive. And it's also going to take the shortest and the easiest path. So they're telling that this is going to work faster than the sigmoid and tanh function. That is the first two functions. And it's also going to be less expensive. That is computationally expensive when compared to the first two types. Okay. And then comes the softmax function. Okay. And then first you should know this is a type of sigmoid function. Sigmoid function is just like, it's similar to the first type. Okay. And then you should learn the equation. Okay. And the value range is between 0 and 1. Nature is non-linear. We know that. Okay. And this is being used mainly in output layer. Just like how sigmoid function is being used in output layer, this softmax function is also used in the output layer. Okay. And suppose if your application is going to be based on binary classification, it is better to go in for the softmax function. Okay. And okay. So this is the third topic. Okay. These are the common activation functions. There are 4 types. Okay. The first one is what? Sigmoid activation function. Then tanh activation function. Then rectified linear unit activation function. And the fourth one is softmax. So these are the common activation functions that are being used. Then comes your McCulloch Pitts neuron. Okay. So it's one of the, this is the first artificial neuron that has been introduced. Okay. And this is a very simple artificial neural network or a simple artificial neuron, whatever be it. Okay. The inputs could be either 0 or 1, or it can also be -1 or +1. Okay. Suppose the input is going to be +1. You can say that the input is excitatory in nature. Suppose the input is going to be -1. You can say that it is inhibitory in nature. Okay. And output is going to be either 0 or 1. Okay. First, we are going to give the input. Okay. And what we have to do is we have to sum the inputs. That's the second part, right? Then comes the summation function, right? So we have to sum the inputs. So what do you mean by sum the inputs? Where we have to multiply it, right? Weights along with the input value. We have to multiply it and then we have to add bias to it. I told you that if the input is 1, it is excitatory in nature. It's going to be -1. See, the second point is wrong. Okay, the input is -1. It is inhibitory in nature. Okay, if it's going to be excitatory in nature, we can add it to the sum. Okay, we can add 1 to the sum. And if it's inhibitory in nature, I told you that input is going to be -1. So 1 has to be subtracted from the sum value. Okay, this is done for all the inputs. Okay, and then finally summation. Summation is what? Calculation. I told you that the product of input value and then the weights, and finally we have to do the summation part. That is plus and minus symbols. With all those things, we have to get the final sum. Okay, and if this final sum is less than some value, that is what they say T is the threshold value or the desired value. Okay, it's going to be less than the target value, the output is going to be 0. And if it's going to be greater than the target value, the output is going to be 1. So that is what is given here. Okay, at the side, at the right hand corner. If the final value is going to be less than the target value or the desired output, then the output is going to be 0. And if the final value is going to be greater than 1, the output is going to be what? The output is going to be 1. Then this is a simple graphical representation of the McCulloch Pitts model. I told you that W1, W2, and W3 are the weights. Okay, W1 and W2 input are +1. The weights are +1. Okay, so it is excitatory in nature. Okay, and W3 indicates that W3 what? It represents -1, right? So it means that it is inhibitory in nature. X1 and X2 and X3. So these are the inputs. And I told you that on the input, the product of this X1 and W1, it's being given as input to the summation function. That is X1 W1 plus X2 to W2 and X3 to W3. This is given as input to the summation function. The output of this is called as, the one which is given to the summation function is called as the weighted sum. Okay. And then if this sum is less, see, T is the summation function or the target value is being stored. Okay. In this thing. And if the sum is less than T or not, that is what we are going to check. Okay. And if the weighted sum is less than the target value, what happens? The output is going to be 0. And if this weighted sum, okay, if it's going to be greater than the target value, the output is going to be 1. If it's going to be less, the output is going to be 0. And if the weighted sum is going to be less than the target value, the output is going to be 0. Okay, and this does not have a feedback loop. Suppose if it's going to have a feedback loop, what we're going to do is what? We are going to update the weights. So based on those updation, we can get the desired output. That is, the target can be achieved. Okay, then some of the examples where this McCulloch Pitts neuron is being used is what? In a NOR gate. We all would have studied in the previous sem, right? In sensors, I think sensors and circuits. Okay, NOR gate. Okay, what is going to be here? They've given a 3-input NOR gate. Okay, how the output of this NOR gate is going to be? If all 3 gates are going to have a 0 input, output is going to be 1. Okay, all the 3 inputs are going to be 0, output is going to be 1. Okay, so that is the output of this NOR gate. Okay, here what they are telling us, it's going to use it's using 2 neurons. Okay, the first neurons, it receives the input, that is 2 neurons is t is equal to 1 and t is equal to 0. This is what they mean, 2 neurons. Okay, so input is being given to the weights are given. Okay, to t is equal to 1, and output is what? The output of the first neuron is given as input to the second neuron. Okay, and then from that second neuron, we get the output. Okay, it's going to have 2 neurons, t is equal to 1 and t is equal to 0. These are the 2 neurons. The input to the first neuron, that is well known. Okay, and then output of this first neuron is being given as input to the second neuron, and then output of this neuron, okay, it depends upon the input that is being given. Okay, and then comes a NAND gate. So NAND gate, what? You know how the output of this NAND gate is going to be. Okay, it gives a 0 when all the inputs are 1. It's just the opposite of the NOR gate. Okay, NOR gate, and all the values, all the 3 inputs are going to be 0, you're going to get an output. Whereas in a NAND gate, when all the 3 outputs are 0, you're going to get a when all the 3 outputs are going to be 1, you're not going to get any output. Okay, that is the difference between NAND gate and a NOR gate. So all 3 inputs are going to be 1, output is going to be 0. Even if one output is going to be 0, you will be getting it. Sorry, even if one input is going to be 0, you will be getting an output. But when all the 3 inputs are going to be 1, you will not be getting any output. Okay, and then next comes the memory cell. So what first we saw was the NOR gate and the NAND gate, where this McCulloch Pitts neuron is being used. Then comes the memory cell. Okay, what they're doing is, what they're telling us, a feedback loop is taken and is given as, a feedback is taken, then it's given to the neuron. It's just going to have one neuron. Okay, a feedback loop is being used here. Okay, and that is being given as input to the neuron. If such a artificial neural network is present, it's called as a memory cell. Here they've given 2 inputs, right? One is +1 and then -1. It means that one input is excitatory and the other one is what? Inhibitory. Okay, and then what happens is what? Because of this +1, what happens is this neuron is being fired. When the excitatory input is being given, your neuron gets fired. Okay, and then because of this inhibitory input, which is -1, I told you that the firing of the neuron is obstructed or hindered. Okay, and then what they're telling, so based on the input, if you give 1 as the input, you're going to get an output. If the input is going to be -1, the neuron is not going to fire, you're not going to get any output. Okay, so the output value at the absence of the inputs is then sustained indefinitely. What this means is, initially they are going to give 1 as the input. Because of that, you're going to get an output. Okay, and that is being given as feedback to the neuron. Next, if you're going to give -1 as the input, even though you're not going to have any input, see what happens is the neuron will get fired. This is because of the feedback loop. So that is why it is called as memory cell. Okay, initially they're going to give the excitatory input. So based on that, you're going to get an output. Okay, and then what happens? This is being given as feedback to the neuron. Now the next type of input is going to be inhibitory in nature. What this input is going to do, it is going to obstruct or hinder the firing of the neuron. Even if no input is being given, your neuron will get fired. What is the reason? It's because of the feedback loop. Okay, so this is called as a memory cell. Even though there's not going to be any input, you're going to have an output. So this is called as a memory cell. Okay, and then let's have a look at the simple neural network for pattern classification. Okay, and the simple neural network, what they're telling us, it's a feed-forward neural network. This is being used for pattern classification. Okay, and then they're telling us what? Let X be the input character and let X denote the inputs and O denote the outputs. Okay, and then what they're telling us what? There are two possibilities of having an output. The first one is binary or bipolar value. Suppose it's going to be binary, the output is going to be what? 0 or 1. Suppose it's going to be bipolar in nature, be it input or output, it's going to be +1 or -1, plus or minus 1. It's going to be binary. Okay, the output is going to be binary in the sense output is going to be either 0 or 1, and if it's going to be bipolar in nature, it's going to be +1 or -1. Okay, so this is the simple architecture of an artificial neural network. Okay, they're telling that small x1, x2 up to xn, that will be the input signals. I've already told about this, right? And what? x1, x2, capital X1, x2 up to xn, that is either going to be the input neurons. Okay, input layer with the x1, x2 and up to xn, they are going to be the input neurons. Okay, here no hidden layers are being used. We just have or we can say that we have n input neurons and we just have one output neuron. N input neurons is x1, x2 up to xn. That's going to be the n input neurons, and we're just going to have one output neuron, which is denoted by y. Okay, and here we do not have any hidden layers. Okay, suppose the output of this if the output is going to be binary in nature, it's either going to be 0 or 1, and if it's going to be bipolar in nature, it's going to be +or -1. Okay, so I told you how the output will be, right? It's going to be the product of the input value and the weights and the input signals or the electrical signals. So that is given as summation of xi into wi, and I varies from 1 to n. That depends upon the number of neurons that are being used in a particular layer. Okay, and then we have, I told you that output is going to be what? It's going to be bipolar in nature. It's going to be +1 and -1. And if it's going to be greater than the target value, the expected value, the output is going to be +1. And if it's going to be less than the target value or the desired value, it's going to be -1. Okay, and then comes the different types of what? These are nothing but the learning algorithms. So first one is, see, I could not prepare the notes for all these, learning algorithms. Okay, we have 5 types over here. I'll prepare the notes and I'll send it by this weekend. The first one is what? I've just given the diagrams for this. Okay, so I'll prepare the notes for architecture, flowchart, and then algorithm and send it to you by this weekend. Okay, the first topic is what? Linear separability. So why this linear separability is needed? Please listen. Okay, we'll finish off the class soon. Okay, I see most of the events are non-linear in nature. Okay, so neural networks, what it will do, it will not give an exact solution. Okay, so it will give only an approximate solution. That is why we go in for this linear separability. Okay, thing. So what will it do? It's going to divide the input space. Input space in the sense, here you can see the lower diagram, right? We got some blue color data and then red color ones. So what it is going to do is, it is going to divide it into 2 regions. That is based on the output, whether it's positive or negative. Let blue be positive and red be negative. So what this linear separability is going to do, it's going to divide into positive region and the negative region. Okay. And for example, see, if you're going to have a 2-dimensional space, we'll be using a line which will separate the points from one class to the other. Okay. So in one class, we'll be having all the red points and the other class will be having all the blue points. That is what we can see here. Okay, so we can say that suppose it's going to be in 2-dimensional space, one line will separate what? The data, that is red points and the black points. But suppose we won't be having a 2-dimensional space. Suppose we're going for a 3-dimensional space. Okay, major. What happens? We have to draw. We have something called as the hyperline. That is what we've drawn. Okay, suppose if you're going for 3-dimensional space, you need to draw this hyperplane or the hyperline, so that it will separate the points into positive region and negative region. But it's two-dimensional space, I told you that we are going to separate in blue color, red color, something like that, okay? Whereas in a three-dimensional space, it's going to separate it into what? Positive region and negative region. So that is why this is called as a linear separable line. That is, by drawing a line, we are going to separate it into positive region and negative region. So now let's see how we are going to arrive at this decision line. And this is based mainly on the neural network itself. Okay, now just consider a simple neural network which is going to have two inputs. Okay, let it be x1 and x2. And then the inputs are being given to, based on the, see this input, this is then given to the neuron. The inputs are x1 and x2. It's given to the neurons, and based on that, you're going to get an output and let it be y. Okay, and I already told you that it will have a bias just to move it to the left or the right. That is moving along the y-axis, something like that. Okay, this is all is used for firing. So input is going to be x1 and x2. Output is going to be what? Based on this x1 and x2, it's going to be y. So what will be the y value of y now? I told you that it's a product of weight and then what? Input signals. Okay, that is x1, w1 and x2 or w2. Okay, it's given in the second figure. Plus the bias value. Bias value is always going to be 1. Okay, now what we are going to do is we need to apply the activation function in order to get the desired output. So what you should do? You should first, we are finding the value of y1. So it's given in what? See, b plus sigma I is equal to 1 to an xi wi. So that is going to be the output. Okay, output of this activation function. Okay, and then what we are going to do is we are going to equate it to 0 such that we can get the value of x2 and x1. So that is given in the second diagram. Okay, such that you get the values of x1 and x2. So based on these values, we are going to draw the diagram. So how we are going to draw this diagram? We can get the value of yn. Y was nothing but the output signal. Okay, output we can get. Okay, and then we are going to equate it to 0. And on equating it to 0, we can get the value of, we can find the value of x1 and x2. So based on these values of x1 and x2, see x2 is going to be what? Minus w1 by w2. X1 is what? If we equate it to 0, these are the values we'll be getting. Okay, x1 is equal to minus b by w2. And based on these values of x1 and x2, you can what? Draw the line such that you can separate it into positive side and positive values in the negative values. Okay. So this is called as the linear separability or linear separable line. It's also called as hyperline. This theorem is called as linear separability theorem. Next comes the what? Hebb net. Okay, the second type. So first one is going to be linear separability theorem or learning rule, whatever be it. The second is going to be Hebb net. Okay, and this is one of the easiest learning rules under the artificial neural networks. Okay, and then this was introduced by a person named Donald Hebb in the year 1949. It was introduced by Donald. So this Hebb net comes under after his name. Okay, so that is why it is called as Hebb net. Okay, and you have something called as Hebb learning rule also. That will come under the second module. So what this Donald Hebb says is what? Learning will occur when there is a change in the synaptic gap. Okay, synaptic gap, I told you synaptic, we saw about dendrites, cell body or soma, and then what? Synapse terminals. Okay, find to the end of the terminals. Okay, they'll have root-like structure. Sorry, you'll have hair-like structures, and to that end, you'll be having what? Bulb-like structure. That is called as your synapse. Okay, and when there is going to be a change in that synaptic gap, what do you mean by synaptic gap? I told you that through this synapse only, one neuron is going to be interconnected to the next neuron. So the gap between these two neurons, okay, that is called as the synaptic gap. Okay, so when there is going to be a change in this synaptic gap, what happens? Your neural network or the neuron, it will learn. Okay, learning will occur. Okay, and there are three main parts. Okay, we all know that, right? We already saw on the neural network structure. Okay, cell body or the soma, that's the center part. I told you, right? We have nucleus in it. Okay, and then comes the axon. Axon is a long connection. You can see. Okay, that is from okay, axon, through this only information will pass, and then comes the dendrites. Dendrites, this will act as the receiver. Okay. And to the other end of the axon, you're going to have the terminals. Okay. Okay. And now to the end of the dendrites, I told you that there's a small bulb-like organ that is called as the synapse. And this synapse is the interconnection between the next neuron, this neuron and the next neuron. Okay. And whenever you have to give some electric impulse or an electric signal has to be given to the next neuron, it is going to be given through the axon or the cell body. Okay. And then what happens? We can say that whenever we want learning to happen in the brain, this can happen only due to the synaptic gap. That is happening in the biological neural network. The same thing is being followed in a artificial neural network also. So learning something in the brain is based on the synaptic gap. Synaptic gap is nothing but the bulb-like structure which is found at the end of the terminals or the hair-like structures. Okay, and the gap that is going to act as an interconnection between two neurons. Okay, and based on that synaptic gap, your neuron is going to learn. Okay, and we have something called as Hebb rule. Okay, I'll give you an example for this Hebb rule. Okay, Hebb formulated this rule. Okay, now if you're going to learn driving, so what we'll do is we're going to learn driving a car. So we'll be so conscious when you're going to turn the car either to your left or right, or if you're going to take reverse, whatever be it, you will be very careful. You'll be watching very carefully. But once you get used to it, or once you get experience, what you will do? You'll be listening to music, or you'll be talking with your neighbor, whatever be it, you will be turning your car to your left or to your right, or you'll be taking reverse. Okay, so it will become a habit. So initially, you're going to learn how to drive a car. You're going to concentrate more, and after learning, you're going to become cool. So Hebb wants to implement the same thing in the artificial neural networks. So he says that, what he's telling, he says that we are going to train the networks. And when the neuron gets trained, initially it will get trained, and later on it gets trained in such a way that it will work automatically. So Hebb wants to implement the same thing, whatever is happening in our brain. He wants to implement the same thing in artificial neural networks. Is telling that when we are going to train the network or train the neuron, what will happen is it will get trained, and later on it will be trained in such a way that it's going to work automatically without any human intervention. Okay, so how we can define this Hebb rule? We can define that when an axon, okay, suppose just imagine there will be two cells, cell A and cell B. Okay, when an axon of cell A is near enough to excite the cell B, okay, then changes will take place. Okay, when an axon or the synaptic gap, it's mainly based on synaptic gap. When the axon of cell A is near enough to excite this axon of cell B, two cells, two neurons are being placed, and the information is being passed to the axon. Because of this, what happens? Your next neuron is going to get fired. And if they are placed very close to each other, okay, because of that, firing will take place. One more thing that has to be noted is what? The type of input. It's whether it's inhibitory or excitatory in nature. So based on that, the next neuron is going to get what? Fired. And this Hebb rule, it will come under unsupervised learning. Okay, this will come under unsupervised learning. And some of the applications of this Hebb rule is what? Pattern association, classification, and so on. Okay. Now this Hebb, I told you about the Hebb rule. This follows two principles. Okay. That is, I told you that two neurons are going to be placed next to each other. Okay. And the interconnection between them, okay, is through the synapse, and the space between the synapse of the two neurons, it's called as the synaptic gap. Hope you are able to understand and you're not getting confused. Okay. And if two neurons are placed next to each other and they're activated continuously or synchronously, then the weight which is associated with the two neurons is increased. Weight is increased. Because of that, signal is being transferred from one neuron to another. Okay. And now, if the two neurons are placed next to each other and if they are activated asynchronously, what happens? Then the weight associated with each neuron will decrease. If it's activated synchronously, continuously, what happens? The weight is going to increase So it's going to, your neuron is going to get fired. But if they're activated asynchronously, what happens? Then the weight associated with the two neurons are decreased. Okay. So based on that only he's formulated a formula. Your Hebb, Donald Hebb has formulated a new formula. What he's telling is the new weights. I told you that weights will increase, right? So new weight will be the sum of old weights and change in synaptic cap. It's fired based on the synaptic cap. Okay. And based on this principle, Donald Hebb has created a new formula which says that new weights are equal to old weights, summation of old weights and the change in the synaptic cap. Okay. Then comes the flow chart. Okay. So under flow chart, first what we have to do is we have to initialize the weights. Okay. It can be 0 or we can give a initial value. Okay. And then steps are performed for each input and output training pair. Okay. We're going to have an input layer and then output layer, right? So that is called as a training pair, input, output, training pair. So all the steps that are going to be followed in this flow chart, we are going to implement it here. Okay. For each and every training pair. First, what we're going to do, we are going to activate the input unit. Okay. So that comes under the diamond box. Okay. So we are going to activate the input units and then we are going to activate the output units. Okay. And then we are going to perform the weight update. I told you the formula, right? New weight is equal to old weight plus change in synaptic gap. Then bias update. So weight and bias will get updated. Okay. And then we have to repeat all the steps for the input output pairs. Okay. And then if there are no more inputs, see, I told you if there are no more, we're going to do it for all the input output pairs. So till the last output pair, if all these computations have been done, all these steps have been followed, like activating the input, output, all those things. Once they have been done, we have to stop the computation. Okay. So this will come under what? Unsupervised learning. So based on this flow chart, we've given the training algorithm. So we can write it by yourself. So based on this flow chart, if it is enough, if you either study the flow chart or the algorithm, you study one, you can do the other by yourself. Okay. So write the flow chart by yourself based on the algorithm, or you can write the algorithm based on your flow chart. So according to me, my suggestion is that you learn the flow chart and based on the flow chart, you can write the algorithm. Okay. So this is the algorithm. So whatever I said under the flow chart, same thing is being repeated here. Okay. And then comes the perceptron. What was the first type? The first type was the linear separability rule, learning algorithm. Then comes the Hebb network. Okay, Hebb net. The third one is what? Perceptron. Okay, and this is one of the most important neural networks, artificial neural networks, and we come under supervised learning model. Whereas your Hebb net comes under unsupervised learning model. In unsupervised learning model, in the sense, it's not going to have any feedback loop. So error cannot be detected. So we are going to train it for all the input-output pairs. And then once all the input-output pairs have been trained, you should stop the computation. That comes under unsupervised learning model. But under supervised learning model, we are going to supervise the model till you get the desired output. Okay, so we can make the necessary changes. How is that done? It's done by updating the weights and the bias values. So by updating the weights and the bias value, based on the error value, we can get the target output or the desired output. Okay, and here there are going to be 4 parameters in the architecture. First one is going to be the input, then comes weight and bias. Under weights, you have this bias. Okay, and the input to the bias is always going to be 1. Okay, and then we have the net input function, and then comes the activation function. So these are the 4 main parameters. Okay, and what of the input values are being given to the perceptron in the neural network. Okay, suppose if you are going to have 4 inputs, there will only be 4 nodes. Here they are given 4 nodes. So they are given from x1, x2 up to xn. Okay, w1, w2, w3, these are the neurons. These are the weights. x1, x2, and x3, these are the input neurons. Okay, and the weights are corresponding weights are W1, W2, and Wn. And here W0 represents your bias. Always the value input to the bias is going to be 1. Okay, that is what it means here. Okay, then comes what? Your net input function. What it's going to do is going to give the summation of the inputs and the weights, and that is being given as input to the activation function. Hope you can understand. Okay, then what? Then comes the activation function. This will help you to tell whether the neuron will fire or not. This the activation function will decide. Okay, and here in this type of perceptron, it was being designed or created by Frank Rosenblatt. He is the person who's created this perceptron. Okay, Donald Hebb was a person who created the Hebb net, and the person who created this perceptron, his name is Frank Rosenblatt. Okay, here he's been using a step activation function. Okay, you can find it out from the symbol that's being given for the activation function. Okay, and once you apply this activation function, what happens is what? You'll be getting an output. Okay, which is then compared with the target value. Okay, then here actually this perceptron, I told you that it's a supervised learning model. Okay, it's a supervised learning model, which means that both the input value and the target value will be given. That is what is meant by supervised learning model. So based on the input, you're going to get an output. That output is being compared with the target value. Okay, if the target value is reached, that's it. Okay, we're going to get the output. If not, we are going to adjust the weights and bias till the target value is being reached. Okay, this is what is happening here. And the same process will be repeated till the error becomes 0. Okay, what do I mean by error over here? It's difference between the target value and the output value. If that is the error. Until the error becomes 0, what happens? We are going to repeat the same process. And one more thing. Here you have two types. Okay, two types of perceptron. One is single layer perceptron. The other one is what? Multi-layer perceptron. The single layer perceptron is just going to have one layer. Whereas multi-layer perceptron, in the sense, is just going to have 2 or more layers in between. Okay, and this type of multi-layer perceptron, I mean 2 or more hidden layers. Okay, and single layer perceptron is just going to have one layer. One layer in the sense is going to represent your output layer. Whereas your multi-layer perceptron, what it's going to do, it's going to have 2 or more hidden layers, and it's being used when you need greater processing power. That is where this multi-layer perceptron is being used. Okay, and then I told you like all the formulas, everything you know. That is the formula to calculate the Yn value. What do you mean by Yn? Yn is going to be the output, right? I told you that X, see from the first diagram, it's going to be X1 into W1 plus X2 into W2 up to Xm into Wm plus the bias value. That is going to be the input of this summation function. Okay, and output of this is going to be given as input to the activation function. Here a step activation function is being used in this perceptron neural network. Okay, and then we have something called the target value or the threshold value, and the output of this function is going to be what? Greater than the threshold value. Output of this activation function is going to be 1. Okay, if the output value is less than the threshold value, okay, then output of this activation function, this you need to remember. Okay, please don't get confused. Okay, you're going to get an output. Okay, and then you have this threshold value or the target value. If the output value you get from this net, the output of this net input function summation thing, it's going to be greater than your target value. The activation function output is going to be 1. Okay, and now if the output value is less than the threshold value, what happens? Your output of this activation function is going to be 0. And now, if the output value is going to be less than the threshold value, the output of this activation function is going to be -1. I told you that activation function, see, it's going to be, see, I told you that it will be either inhibitory or excitatory. So if it's going to be 1, it's going to be excitatory in nature. It's going to be -1. It's going to be inhibitory in nature. And with 0, it means that you're not going to get any output. So nothing is going to happen to the neuron. Okay. Now, then I told you that we are going to compare it, right? And then if we don't get the target value, what we are going to do? We are going to update the weights and the bias. Okay, that is happening because of the error signal. Okay, that is because of the feedback loop. That is why it is called as supervised learning. Okay, values are compared, target value and the output, that is desired output, and the output that we get, both are compared. Okay, and if the difference, if there is going to be some difference, based on that difference value, that is called as the error value, the weights and the bias are getting updated. If the difference is going to be 0, that is, if the error is going to be 0, computation can be stopped, which means that that is the final value of the weight and the bias. It will not get updated after that. Okay, so this can be taken as the, so once error becomes 0, the output that we will receive can be taken as the final output. Hope you understand. The same thing is being repeated for all the models. Okay, then comes the flow chart. Okay, the same thing is happening. First is what we need to start the computation. Okay, then the same thing is only being repeated, whatever we saw on the previous slide. Okay, we're going to initialize the weights and the bias. Okay, and then we have to set the learning rate, that is between 0 to 1. That is given by alpha. Alpha is called as the learning rate. Okay, rate at which it learns. Okay, that is the learning rate. We set between 0 and 1. And we need to do this process. This process has to become done for each and every input-output pair. So we call it input-output training pair. Okay. First, what we are going to activate the inputs. Then we have to calculate the net input. Activate the inputs is what? We're going to give the inputs x1, x2 up to xn. Then we have to calculate the net input. How is it possible? This is possible by what? Multiplying what? The input value and the weight value. We saw this in the previous lecture. Okay, it will be x1 w1 plus x2 w2 and then up to xm wn m, and then we are going to add the bias to it. Input to the bias is going to be 1, so it's going to be 1 into b. That is how we can calculate the net input function. Then you have to apply the activation function. Okay, activation function is what? Step function. Okay, and then comes the target value. What we're going to do is we're going to check it with the target value. If the target value is reached, if it's equal, target value and the output is going to be equal, there is not going to be any update to the weights and the bias. Whereas if you're going to get some error, in the sense, if there is going to be some difference between the target value and the target value and the output that we've got, then we need to update the weights and the bias. Both we need to update. Okay, and then this update has to be given as input to the neuron. Okay, next neuron, and then comes the summation function. Everything. This process is repeated. Okay, till the target value is reached. What is the reason? Till the target value is reached. This is a supervised learning method. That is why till the target value is reached, this whatever process I told you, right? We have to activate the input function, calculate the net value, that is summation function. Then we have to apply the activation function. All those processes have to be followed. Okay, till you reach the desired value or till you get the target value. Okay, the reason behind this is what? This comes under unsupervised learning algorithm. Okay, and once it has been reached, if the target value and the the output value are same, it's equal, then you need not update the weight and the bias value. Okay, so that will be the final value, and you will also be getting the final output. Okay, so the fourth type is, they just have 2 more types. Okay, we will finish off with another 5 or 10 minutes. Okay, then the fourth type is what? It's called as Adaline neural network. It's also called as what? Adaptive linear neural. ADA stands for adaptive, LI stands for linear, and NE stands for neural. Adaline neural. This is called as Adaline network, not Adaline neural network. I'm sorry. Okay, this is Adaline network. Okay, here you have what they're telling is what? You will be having a computation, that summation part, right? That's a computational unit, summation thing. Okay, this is going to have a linear activation function. Okay, so that is why it's called as a linear unit. Okay, so from this only comes the name Adaline. Adaline stands for Adaptive Linear Neural Network. Okay, and then here in Adaline Neural Network, you're just going to have what? A single linear unit. Okay, we're just going to have a single linear unit. We're not going to have any hidden layers or any other layer. You're just going to have a single layer or single layer network. That is, you're going to have this output layer, one output neuron with one, and that is called as an output layer. And then you have this input layer. Okay, that is one of the reasons. And one more thing is what? The relationship between the input and the output layer is linear in nature. Okay, and we have something called as what? Activation function. I told you, right, about the activation function. This is going to use what? Bipolar signals. Okay, that is, it's going to be the terms of +1 and -1. Okay, so this is the what? Architecture of Adaline neural network. This x is equal to 0. X not is 0 represents your bias. Okay, I already told you that the input to the bias is always going to be 1. Okay, so it will be 1 into B. X1 is going to be the input, and then the weight associated with it is going to be a W1. So the product is going to be X1 into W1, okay, plus X2 into W2 and X into W1. And the summation of these products, that is weights and the bias, is being given as input to the summation function. So output you can see, right? Output is going to be what? Y is equal to B plus sigma Xi Wi. Okay, this value is then be compared with your target value. Okay, if both are equal, you'll not be getting any error. If it is not equal, you'll be getting an error value. Okay, and based on this error value, we are going to what? Update the weight and the bias. One more thing you have to notice here is, see, example, if they're going to consider 3 inputs. At a time, they're going to give 3 inputs. Excuse me. They're going to give 3 inputs. We can also call this as 3 examples. Okay. So we're going to have 3 inputs, right? So these 3 inputs will be given random weights. Initially, it's going to be 0. But it's going to have random weights, okay? And then these inputs, I told you that they're going to be given to the summation function, and then the value of the output is calculated. Okay. We then compare it with the target value, and if there is any error or difference between the output value and the target value, you're going to update the weights, and the formula for updating the weights also is given in the diagram. The same thing, you're going to update the bias value also. Okay, and the same step is being repeated for the 3 inputs, or you can also call as 3 examples, whatever be. Okay, so once it has been completed for 3 inputs or examples, you call it as one epoch, EPOCH. One epoch is being calculated. Okay, and based on that value, we are going to calculate the errors. That's the formula they've given them. How to calculate the error for each and every epoch? Say they've given it. Okay, so they're going to give 3 inputs or 3 examples. They're considering it as one epoch. Okay, and now before going to the second epoch, that is the next 3 values. Okay, what they're going to do? They're going to calculate the sum of the errors, summation of the errors. Okay, and based on this value, we are going to decide whether to go for the next epoch or not. Okay, and if the error, that's we're calculating the error, right? If that error is within the acceptable range, okay, then we can stop with one. We have something called as the error range. Okay, we're going to give 3 inputs, and based on that, we're going to get the outputs. Okay, and before going for the next 3 inputs, we are going to calculate the error using this formula. Okay, and if the value of this error is within the acceptable range, okay, it's within the acceptable range, you can stop it with one epoch itself. If it's not within the acceptable range, so they're going to take the next 3 inputs. Okay, that is called as the second epoch, and all these steps are being performed. All these computations are being performed. Hope you understand. Okay, Adaline neural network is done for every epoch. In this Adaline computation is done for every epoch. Epoch in the sense 3 inputs are being taken, or you can also take it as 3 examples. Okay, it's being given as input in the summation function. Okay, and once 3, based on these values, we're going to update the weights and the bias. Okay, and once computation has been done for 3 inputs, we are going to calculate the error. Now, if the error comes within the acceptable range, what happens? We can stop with one epoch, and whatever output we are going to get, we can accept it. If not, we have to go forward with the second epoch. That is, the next 3 values have to be considered. That has to be given as input in the summation unit, and then we're going to get an output. The same process is being repeated. Okay, same process is being repeated. So till the previous neural network, we saw that we're going to take the value we're going to take the output, and then we're going to compare it with the target value, and then based on that difference, we are going to update the weights and bias. But here, they're going to consider the same thing is happening, but they're going to take 3 inputs or 3 examples. Okay, after 3 inputs are being taken and the process is repeated, they're going to calculate the error, and they're going to check whether that error is within the acceptable level. If it's within the acceptable level, they'll be stopping the computation, and the output that is obtained is being accepted. If the error is not within the acceptable value, again, they're going to continue with the next 3 values of input. So at a time, they're going to consider 3 values or 3 inputs over here, but that is not so with the previous. That's okay. So this comes under the architecture of Adaline neural networks. And then comes the flowchart. Same thing is happening here. First, we need to initialize the weights, bias, and then I told you about the learning rate, right? It lies between 0 and 1. Then we have to set the acceptable error limit. Okay. But this step is not being included in the previous method. Here we are giving the acceptable error value. That is done for every 3 inputs. Whereas in the previous method, we're going to check the difference between the target value and the target value and the original output. Based on that, we're going to get the output. But here, we are going to do it for every 3 values. Okay. And then, yes, because of that, we're going to set an acceptable error. Okay. And this is being carried out for each training pair. That is 3 times it's being carried out. Okay. And based on the output you're getting, we are going to update the weights and bias. I'm repeating the same thing again and again. We are going to update the weights and the bias, and then we are going to get an output. Okay. And based on this output, after 3 inputs, we are going to check the error. And if the error is within an acceptable limit, we are going to stop the calculation with that epoch. That is 1 epoch in the sense 3 inputs. If the error is not within the acceptable value, what we have to do is we need to go in for the next 3 inputs. And the same process is repeated till the error comes within the acceptable value. Okay. And this is a flowchart, and the algorithm will be the same. So you can write it from the flowchart itself. Okay. And then comes the what? Last type is what? Madaline network. Okay. Madaline network, what this is called as multiple adaptive linear network. Adaline stands for adaptive linear neural network. Madaline stands for multiple adaptive linear network. Okay. Here, what they're telling us is going to consist of many Adaline units, that is hidden layers, and then a single Madaline unit. That is, we all know that we're going to have an input layer, input unit, and an output unit. In between, you're going to have many hidden layers. So what they're saying here is, in the Madaline network, this input layer is what? X1 and X2. That is going to be an input layer. This Y stands for the Madaline layer. Okay, that is the output layer. You're just going to have a single output unit or a single output layer. But in between, you can have n number of hidden layers, not hidden neurons. You can have n number of hidden layers, or the hidden layers are called as Adaline units over here. Okay, so one more thing they're telling is what? See, here you can see just one hidden layer, Z1 and Z2. Okay, these are the hidden neurons, Z1 and Z2. And the weights that are connected from Z1 to Y and Z2 to Y, that is V1 and V2, are fixed in nature. And they're going to have equal values. I told you that for the previous methods, all those methods, weights can get updated. It should be updated. Weights and bias are being updated, mostly the weights, okay? Whereas in a Madaline network, okay, the final part, that is the final connection between the Adaline unit and the Madaline unit, that is the last hidden layer and the output layer. So the weights associated with it are going to be what? Fixed, and they're going to be positive, and they're going to have equal values. So that thing you should not forget. Okay, but the weights between the input layer and the other Adaline units are nothing but the hidden units over here. Okay, that weights can be adjusted, or they should be adjusted during the training process till you get the desired output. Okay, as usual, your bias value is always going to be 1. Okay, hope you understood. Madaline network is what? It's also called as, it is the full form of this Madaline is what? Multiple adaptive linear network. Okay, it consists of what? One output layer, that is output layer is also called as Madaline layer. It's going to have one input layer. We don't have any name for that. It's given by, denoted by X1 and X2. And you can have n number of Adaline networks, Adaline layers. Adaline layers are nothing but, here they represent the hidden layers. Okay, and the weights between the input layer and the Adaline layers, that is hidden layers, they have to be adjusted such that you get the desired output. Okay, whereas the weights between the final Adaline network and the Madaline network, that is represented by or denoted by V1 and V2, it's going to be what? Fixed, it's going to be positive, and it's going to have equal values. That is V1 and V2 are going to be same. One more thing you have to remember here is bias input to the bias. It's always going to be 1. Okay, and then it comes the training process. It's very much similar to that of your Adaline network. Okay, so the same flowchart can be followed. Okay, that's it. So we just brushed up with the first unit. Okay, and just one more topic. Okay, that is simple applications for all these networks. That thing alone we need to study. Okay. And I'll just send the notes for these topics by this weekend. Okay, please go through it. Monday's class, if you want, we can just discuss. I'll take once again, okay, in person. If you're not able to understand, please let me know, because there's no other option. Okay, just because I need to take online class.